All right, we're back. We are on page, what are we on? Page 5 of notes 12 of Calc AB. We're doing definite integrals, geometric approach. So we're just really finding signed areas. We've learned a couple properties of definite integrals, and in this problem, we're going to do some more. So first question we want to do is the definite integral from -6 to 6 of f of x dx, which is kind of like this whole thing. So let's like divide this up and find some regions. I'm going to cut this here. So this is half of this rectangle. So that's going to be 1. And then I'm going to cut it here. I think I'm going to have to cut this in a different way for some of the problems, but I don't know. We'll find out. This is definitely 6. I'm just counting boxes there. This one's going to be 2. And then we got some nice symmetry going. So this will be -2. This will be -6. So this is actually an odd function, which hopefully we'll get to take advantage of at some point. But who knows? So these are my regions so far. So -6 to 6. Oh, well, I just mentioned this is actually an odd function. So since it's odd, the integral from like -a to a is just going to give you 0. So this is going to give me 0. If you would prefer to do the work, you could add these up and get 9, add these up and get -9, and then 9 plus -9 is 0. But you should definitely do it by looking at it and saying like, oh, this is an odd function. All right, so the next part. So the location of the absolute value matters a ton. So this is going to be the integral from -6 to 6 of the absolute value of f of x, right? So it's not the absolute value of the definite integral, it's the definite integral of the absolute value. So what we want to do is we want to go up here, and basically anywhere that this graph dips below the x-axis, we're going to reflect it up because it's negative. Its absolute value is the opposite of that. So we're going to end up here, and then over here, and then here. So this -9 that was down here ends up here as +9. So this is just going to be 9 plus 9, which is 18. So I actually, we don't really need to look at it for everything, but I did, in GeoGebra, I created this graph. And was it annoying? Sure. But might it be useful? It might be useful. So what we can do is we can take a look at things like the absolute value of f of x, right? And so you can see, let me turn off f of x. You can see that what happened was where f of x was negative, it's reflected up. So if it was -9 down here, it's reflected up, and now it's +9 up here. So what's nice about doing this is that I can now like create these functions so we can take a look at them if we need to like further convince ourselves. And you can, if I remember, I'll put it in the description. I won't remember. Somebody's got to like comment that or let me know or whatever. All right, 2 times f of x. So now here's another thing, like what are we doing? We are doing the integral from 0 to 6 of 2 times f of x. So think of your transformations. What does that do? Well, 2 times f of x is just going to take every height and make it double. So, you know, this is going to end up here, here. This is still going to be 0. This will end up down here, and then this will still be 0. So one thing that we could do is we could actually do that. So I'm going to do it in a different color. So here, I only need 0 to 6 though. So I'm going to do this. And then we'll talk about a different way to do this that is definitely a better way to do this. Because the transformations work, but like you don't want to be doing this every time, right? This is pretty annoying. So focus on the like green regions here. So 2 by 4 is 8, but you only get half of it. So now it's -4, which if you look is double this. And then we're going to get 3 by 4. So that's -12. But if you look, that's double this. And then I bet that this is going to be -2, which is double this. And so it's 1 by 4. So yeah, this will give me -2. So it actually is the case that to find this area, instead of doing what I did, which, you know, what I did isn't wrong, but what I did was kind of annoying because you have to like graphically do it. You can actually just do, it's called the constant multiple rule. Just take it out. You can factor out a constant multiple. So a constant can come out. If it was an x, you can't take it out. Anything that's related to x because of this is stuck in there. You can't take it out. But you can pull out a constant, so it's really just this. So this is really just 2 times -9, which is -18. Okay, so for the next one, I definitely don't want to create this graph. I'm not going to create it on my own. I'm going to go to GeoGebra and show you. So f of x over 2. So think about your trig functions. Like, what does the sine of x over 2 do to the period of the trig function, right? So the period of a trig function is 2 pi of sine, at least, is 2 pi over b. If b is 1/2, it's 2 pi divided by 1/2. It's now 4 pi. It got bigger. It stretches it horizontally. That's what's going to happen here as well. So I'm going to graph f of x over 2. So I graph f of x over 2. Let me zoom. And everything has been stretched out, which is kind of hard to see, I guess, maybe. There's no vertical changes. It's all horizontal. Like the point that was at 6, 0 is now at 12, 0. The point that was at 5, -2 is now at 10, -2. The point that was at 2, -2 is now at 4, -2, and so on. Everything has stretched. I could stretch the graph and then actually do the problem, go from -6 to -4. So -6 to -4 is like this. It's a rectangle. It's actually a square. It's 2 by 2, so it should give me 4, right? I want to do this in a different way though, because I don't want to have to stretch that graph. So what I would rather do is like the most powerful technique that you're going to learn for definite integrals, I think. I mean, I'm kind of making that up, but also I think I'm serious. We're going to do u-substitution on this. So u-substitution means pick u. The thing you pick for u is almost universally going to be the thing inside the parentheses. So I'm going to say that u is equal to x over 2. Okay, what impact does that have? Well, it kind of has a lot of impact. If u is equal to x over 2, then we know that x is equal to 2u. So this is a big idea. We're going to find something called a differential. So a differential is this. This is the differential, just dx. The way you can find a differential is sort of just by taking a derivative. So what I'm going to do is I'm going to say the differential of x is dx, and the differential of u is du. So x is a function of u. If you look at this, x is a function of u. So you would be finding dx du, and then it's like you bring the du over to the other side. Some people really hate that interpretation. I don't hate it at all. So we get this. So now what I can do is I can substitute, where I see x over 2, I can make it u. Where I see dx, I can make it 2 du. The problem, it's not really a problem, it's not a problem yet until we mess it up. The problem is, because this is dx, this is x equals -6, and this is x equals -4. And what we're doing is we're changing everything to u. So if I'm changing everything to u, then when x is equal to -4, u is going to be -4 divided by 2. So I'm just subbing in here. -4 divided by 2 is -2. And when x is -6, u is going to be -6 divided by 2, -3. So I can actually change this integral, and this is where the magic happens. I'm going to change the whole integral into an integral in terms of u. What? So this will be a -3, -2. Kind of like a pro tip. When you're changing these, change them in like the relative locations, right? So do the top one first and then the bottom one next, so that it goes in the top and it goes in the bottom. I mess that up sometimes, and I'd like to not. And so that's why I've kind of tried to do that. And this. So that becomes f of u, and then dx is 2 du. So we're almost done. It's like a lot of prep work, but then it's a little easier to do. Also, remember, we think the answer to this, I think, is going to be -4. No, +4. I think the answer is 4. So I'm going to do the constant multiple rule and take 2 out. -3 to -2, f of u du. Okay, now how does this help us? Well, this is the graph of f of x. But like x is just how you spell the variable. It could be the graph of f of t, f of q, f of r. It doesn't really matter. It could be the graph of f of u. And if it's the graph of f of u, I need to now find the area between -3 and -2, which is definitely 2. So I'm going to say this is 2 times, so 2 is still there, 2 times 2, which is 4, which is what we got on GeoGebra when we stretched out the graph. This method, when you get good at it, crazy fast and accurate. And you don't have to do the thing where you're like changing the graph. Changing the graph is sort of generally a bad idea, I would say. It's like, what are you going to do? You're going to draw every one of these graphs? That's a nightmare. So let's see if we can do the next one in the same way, right? So what I would expect to happen graphically is that this transformation is going to horizontally stretch our graph by a factor of 3. I don't want to do that. So instead, I'm going to do my substitution. So usually, the thing you choose for u is going to be in there. So, and like u-substitution, it gets complicated. Well, not complicated. It gets more complicated, I guess I should say. So I'm going to start with u is equal to x over 3, which means that x is equal to 3u, because we need to sub for dx, we need to sub for x over 3, then we need to sub for x equals -3 and x equals 6. All of our x's need to become u's at this point. So dx is 3 du. That's good. If x is equal to 6, then u is equal to 6 over 3, so 2. And if x is equal to -3, then u is equal to -3 over 3. Okay, thank God. I thought I was going to have to like use a fraction and then find like a fraction of a box, and that was going to be annoying. This would be -1. So are we ready? We can sub for this, we can sub for this, and we can sub for those. Yeah, I think we're ready. So let's rewrite this. So I'm going to just use the constant multiple rule right away. That 3 from the du is going to come out. We have a -1 here, we have a 2 here, f of u du. So we go up to the graph, we're going to do this definite integral, -1 to 2, and then we're going to multiply by 3. So let's see if we can do it. What was it? -1 to 2. Why? -1 to 2. You know, I'm going to erase this one just to kind of like not helping right now. Okay, -1 to 2, maybe a different color. So we need to go like here, and then, so that part. Okay, so this is half of 1, so this is 0.5, positive 0.5, -2, positive 0.5, -2. Maybe I'll write that. So here we have 3 times 0.5 minus 2. And what does that give us? I don't know, -1.5, -3 halves, -9 halves, -9 halves, I'm going to say. And we could check that actually on GeoGebra if we wanted to. So I'm going to check that one and then maybe cut the video and come back and do the rest of these in the next video. So let's see, we want to go, I'm going to hide this, and then I will graph. So I'm going to do 2 things. I'm going to graph f of x over 3, like super elongated, right? And now I'm going to ask GeoGebra, GeoGebra can find definite integrals. I'm going to do the integral of this function is called t, and I need to go from -3 to 6, and it might work. Okay, -4.5, which is what we got. Awesome. I also, and you can see it like shades it in for you. It's like very cool. I mean, I definitely recommend you play around with that. So let me hide, so that's -4.5. That's on this elongated graph. Now what we did was we did the integral integral of f from -1 to 2, and we get -1.5, but then we multiply by 3 because our u-substitution and our du gave us a constant multiple of 3, so we end up at -4.5. Both approaches work. It's just that from like a actually doing the problem standpoint, I think you will find the u-substitution is way easier because you don't have to recreate graphs, which can be a giant pain in the neck. And then you have to do the geometry on the new graph. It's like, it's a lot of steps. All right, so we're gonna stop here, come back in the next video and do the next bunch of these. So yeah, I think that's the plan. So I'm just trying to find the stop button. There we go. All right, see you in the next video.